in this one we'll talk about Lagrange theorem, which is an interesting theorem in abstract algebra, and it concerns the magnitude of a group, namely the amount of its elements. In other words, in the relation to that group's subgroups. So if we have an arbitrary group G, and I'm not going to really go into the definition of what a group is and what a subgroup is. If we have a group G, this is the notation we use when we want to say H is its subgroup. So H as a group is the subgroup of G. Okay, I could do a quick repetition of some brief reminder of what it means to be subgroup of a group. So basically, to be a group, a set, the underlying set of elements of that group G, for it to be considered a group, must satisfy the group axioms. The subgroup also satisfies them, but the subgroup is basically some elements from G. It could be all of G, that is just a trivial example of a subgroup, or just the identity element, that would also work, of G, or some proper subset of the underlying element set of G. But still, what has to be satisfied in order for it to be a subgroup, for it to be recognized as a subgroup, is that H, for any of its elements, the binary operation between them will result again in one of the elements, again inside H itself, inside the underlying set of elements within H. It won't jump into the rest of G. And also, if H is defined as just some elements of G, it will, the operation between them will basically result in elements again inside H. Not in some element that is in G but not in H. That cannot happen, and it wouldn't be a subgroup. And also there's the same identity element, if one thinks about it. And of course all this stuff can be proven, but this is a quick reminder of the basic properties. Then there's, of course, for every element inside H, one can find the inverse to it, according to the group's operation of G, because it also carries the same operation as its group, whose subgroup it is. So for every element inside H, again, there's an inverse inside H again itself for it. And it, as I said, it can be just the identity element of G, it can be all of G, or it can be a proper subset of the vertex set of the element set of G. Alright, so let's go into Lagrange theorem. What it talks about is basically very nicely said, or very simply said. We can express it as the fact that if we have a group and a subgroup and both are finite, so we can count the number of elements in these groups, then a subgroup divides the order of a subgroup, meaning the number of elements of a subgroup divides the order of the group whose subgroup it is, namely the number of elements of the group whose subgroup it is. So if there's a group and there's a subgroup, that subgroup divides the number of elements of the group whose subgroup it is. I can write it very briefly, for example, like this. This is the magnitude of H of the subgroup of some group G. And then this vertical bar, as notation, means divides. And now in this vertical bar notation again, I write the group G. So this denotes number of elements inside H. This says divides, and this says number of elements inside G. Alright, so now let's think about an example. So an example could be, for example, Z sub 8 with addition, which is a group of 10 elements, namely the elements that is 0 through 9, integers, positive integers. Well, it's, I could say, plus sub 9, for example, plus sub 10, by which I mean addition modulo 10. So whenever I add some of these numbers, I then divide it by 10, and the remainder is the result of the operation. So the operation between two elements of the underlying set of this group is I add two of the elements, and after I add them, what is their remainder after division by whatever this modulo at the sub-index of pluses is 10. For example, 5, and then another 5 in operation with itself results in 10. And I divide by 10 and find the remainder, which is 0. So 5 plus 5 under this group's operation will be 0. 7 plus 7 will be 4, 9 plus 9 is going to be 8, 7 plus 8 is going to be 5, and so on. Alright, and of course if the two numbers add up to less than 9, less than 10, then it's like normal arithmetic. So 0 plus 1 is 1, 2 plus 3 is 5, and so on. Alright, so that's our group and subgroups of that. Well, Lagrange theorem tells us that subgroups can have an order that divides the order of if there's a subgroup of a group, it must divide the order of the group itself, whose subgroup it is. So this group, this Z10, let me just for now, in a quicker notation, I'm going to write this all parentheses, but just this, I'll say its magnitude, these vertical bars means magnitude, meaning number of elements in that group, is 10. Alright, so what numbers divide 10? Well, 10 itself, so there's the whole group itself. Of course, a group is a subgroup of itself, so we just take all its elements again, nothing has changed with trivial scenario. Also, 1 divides any positive integer. So the trivial subgroup of just the identity element, if I just say 0 as the only element of a possible subgroup, because the identity element under addition, even under modulo addition, is 0. So a group of consisting only 0 under the same operation of addition or modulo addition to be exact, where with the 0 it doesn't really show anyway. So, but we should retain the same operation when looking at the subgroup. So that's a trivial subgroup if it was just consisting of the element 0. I mentioned the case where it's the whole group itself. Well, that's these two trivial ideas of subgroups that basically are automatic subgroups in any case. And what about non-trivial subgroups? Subgroups on element consisting of an underlying element set that's a proper subset of the set of the original group. Well, that could have either 5 or 2 elements. So let's see what those are. So what about the group 0, 5? Two-element subgroup, all right, or 0, 2, 4, 6, 8. What about these two groups? Well, it turns out that they are subgroups of this group. We can see that if we add any two elements, it will end up again in the group, especially under modulo 10. So 4 plus 8 under modulo 10 addition is 2, again ending up in the group, and so on. Well, if we look closer at this through number theoretical lens, then we find an exact reasoning for it. We will add these numbers and we'll see that actually yes, the chosen elements, so these are both subsets of this underlying set of the Z10 originally. The way we chose these numbers, well, first of all, we knew that if there's a subgroup, its order must divide the order 10 of the original group, but also we didn't want to choose the trivial subgroups, which would have either the whole 10 elements or just one, the identity itself only. So we had the option of 2 or 5 elements. And now, if we look at it through number theory lens, we can reason out why this works. Well, we need to resatisfy the axioms of a subgroup of a group for that subgroup. It must work again that any two added elements end up in the group again, end up as an element, the result of that operation between any two elements ends up an element of the group again, which happens both here and here. Here, 0, 5, well, add it and it's still 5. There's actually not much space for some other chance of example than that. Well, 5 plus 5 is 0, and 0 plus 0 is 0, 0 plus 5 is 5. So everything ends up in the group. 0 is the identity element, so it's the inverse to itself, and 5 is the only other element, non-zero element in the group, and it's actually also inverse to itself. So that's satisfied here. We also have always an inverse, right? So the way we structured it here is we've picked correct elements, and we can look at it closer through number theoretical lens to reason out why. So why the subgroups have these concrete elements, but here we just look at the Lagrange theorem. We're just reminding ourselves of Lagrange theorem from this exact example. There's not much of a further goal for us here. Now, so I just put these bars around the sets, right? Both of these are subgroups. Let's say this is H1 and this is H2. So H1 is our first subgroup, And both are going to be subgroups of G, just to make sure that we clearly state it, right? So this doesn't look like some arbitrary sets. We actually know what they are. They're both subgroups of G, and they're consisting of proper subsets of the underlying set of G. They're not just trivial subgroups. All right. So these two work, and let's remind ourselves. But we've already looked at them. We've already realized it many times. But just before I delete this, let's realize that yes, indeed, it's true. The number of elements of H1 is 2. The number, I put these bars around the set notation just to say, okay, so how many elements there are? I just count them, right? 5 here, 2 here. I mentioned it before, even running down the concrete elements. But both these numbers divide the original Z10. Well, I can also put it around here, right? The original 10 elements of that group, whose subgroups they are. So that's satisfied. So Lagrange theorem verified here with an exact example for this group. I mean, we've looked at an example and I saw that the proper subgroups, yes, their order also divides 10, because 10 is of course divides trivially itself, and 1 also of course divides trivially an integer. So that wouldn't be much of a challenge, and we also know how those two trivial cases of a subgroup look. So here we saw non-trivial cases. All right, so that's that. And now let's also look at it in the context of cosets. So, I mean, we could retain the Z10, right? The Z10 here, I could just keep it and look at something further. There's something called cosets, and that's also an abstract algebra concept. And it's about basically taking one element from a group and then running it in operation with all of the elements of its subgroup. So what I could do is say, now I just choose the group H, which is 0, 5, let's say that's H1. And of course, I'm writing again what had been written before, but H1 is obviously a subgroup of G. And cosets, well, as I said, are basically sets of operation of taking an element of the original group G and putting it in the group's operation, binary operation with each element of the subgroup. So a coset, and it's denoted, and we are going to now be talking about left cosets. If the group is abelian, doesn't matter left and right coset, but when order of operation matters, then it can be differentiated. So now let's talk about left cosets. Left cosets is basically denoted as such. What it basically means is we will take one element from the original group G and put it in operation with each element of H gradually. All right. So what will it be? Well, if we set one element of G, let's say 0, and put it with each element of H, well, it's just 2 elements, so that's going to be 0 plus 0 and 0 plus 5, so 0, 5. That's the same. That's equal to actually this group itself. Then I can add, all right, so I can just write like this, cosets, and I'll just list them as sets. So if I choose another element from G is 1, so it's going to be 1, 6. Then I choose 2 and put it in operation with each element of the subgroup, so 2, 2, 7. And I continue as follows. 3, 8, 4, 9. And then I end up with 5, 0 again, which I will not do. And if I go higher, we can verify, but I have to if we go higher, then we will get the same results that we already gotten, all right? If I go to 6, 7, 6 and 11, but more 10, so 1, so 6, 1, and we already had it, all right? So we see the number of cosets, we can count it, is 5. And Lagrange theorem not only says things about, and that's why I'm showing, Lagrange theorem, one more point in this video. Lagrange theorem not only talks about the number of elements of a subgroup in relation to the original group, and that the ratio of them is an integer, but also that the same property applies for the number of cosets that are disjoint. All right, so the moment they start repeating, we don't count them anymore. So if we count cosets, which are basically, again, taking one element from G and running it in operation with all elements of the chosen subgroup, the number of these cosets is going to divide the order of the group, and that's true. We have 5 and it divides the order of the group because it divides 10. The order of the group is 10 of the original group G. And I mean, we can also take H2. How many are there going to be of those cosets? Well, H2 was 0, 2, 4, 6, 8. And if we do, well, I can write GH1 for cosets based on H1. And we can see a pattern. Before we had 2 subgroups, we found a subgroup of 2 elements, a subgroup of 5 elements. And we see for the subgroup of 2 elements, we have 5 distinct cosets. And you can perhaps already guess, for the subgroup of 5 elements, we will have 2 distinct cosets. Let's see. So take it in operation with each element of G, but take just one at a time from G and put it in operation with all of H. So the first coset is 1, 3, 5, 7, 9. The second coset will be 2, 4, 6, 8, 0. But now we see 2, 4, 6, 8, 0. That is the same as we had initially. Alright, that's the same. Here it also happened, one of the cosets, because there's 0, the additive neutral element, identity, we also had the same as actually the subgroup. We had a coset of the same being the same set, but as the underlying set of the subgroup, here we also have the same thing happening. If it's an odd number from G added to all of members of H2, we have a thing that's a distinct set from the H2 itself. But if it's an even number, we see it ends up being the same as H2. If I have 3, so 3, 5, 7, 9, 1. But 3, 5, 7, 9, 1 is just a different ordering. It's the same as the first coset we had. And we see, so there's just 2 distinct cosets based on the subgroup H2. And again, Lagrange theorem says, the second thing of Lagrange theorem says, just like G was divided, the order of G was divided by the order of its subgroups, if for finite groups. We also have another fact closely related to it, the number of cosets. So let's say we're now talking left cosets of a subgroup inside that group is also going to, of distinct cosets of a subgroup inside the original group, divides the order of the original group as well. Here we see the numbers are same. Here concretely, here the distinct number of cosets is 2, and that divides 10.